You know that car sitting in your driveway? Right now, it's going through the biggest change in over a century. And what's driving it isn't the engine, or the horsepower, or the slick new design. Nope, it's being driven by millions and millions of lines of code. And that really brings us to a huge question. What is the single most important make or break decision a car company is going to make in the next 10 years? It's not about batteries, it's not about speed, it's a software choice that will literally define their success or failure for the next 15 years. Because first, we have to get our heads around a fundamental shift. The machine we've always called a car, well, for all intents and purposes, it's now a seriously powerful computer on wheels. And that leads us to this core concept, the software-defined vehicle, or SDV. Now, this isn't just a car that has software. It's a car where its features and its functions are enabled by software. Think about it. Heated seats you can subscribe to for just the winter months, or a performance upgrade you can download overnight. That means picking an operating system is no longer just a technical detail. It's a 15-year strategic bet on what that car can become. So, what's the end game here? What's the big prize? It's all about reaching what the industry calls level 5 maturity. That's the holy grail. It's where the car stops being just a car and becomes a true platform for innovation. I'm talking about an app store for your vehicle, right? You could integrate third-party services, pay for your coffee from the dashboard, find and pay for parking, all of it generating revenue long after you drove it off the lot. And that is why the underlying OS is so incredibly critical. Okay, but this new reality, it creates this massive, fundamental conflict for an industry that has always put one thing above absolutely everything else: safety. Let's dive into this dilemma. To really get one side of this conflict, you have to understand this number: $8.8 trillion. That's what Harvard researchers say the open source software ecosystem is worth. This isn't just about saving a little money anymore. It's a massive strategic lever for innovation. And the undisputed king of that ecosystem is Linux. Car makers are absolutely flocking to it, and for some pretty irresistible reasons. You get instant access to a global talent pool. It's been battle-tested in everything from SpaceX rockets to the world's most powerful supercomputers. And it frees you from being locked into a single supplier. But the real killer feature? Speed. Development that used to take weeks can now literally be done in a matter of hours. And this is the heart of the paradox. On one side, you have the world of Linux. It's all about rapid innovation, constant change. We're talking over 500 security patches a year. Its whole philosophy is about building good software fast. But on the other side, you have automotive safety standards, like ISO 26262. That world is the exact opposite. It's static, it's frozen, it's rigorously certified. Its focus isn't on how to build good software, it's on how to prevent harm when that software inevitably fails. These two worlds are just fundamentally at odds. This leads to what might be the perfect metaphor for this entire problem: trying to make fast-moving, ever-changing Linux comply with these slow, static safety rules. It's like trying to install snow chains on a moving Formula One car. It just doesn't work. It's a total clash of purpose, pace, and philosophy. So, how in the world do you solve an impossible problem? Well, the brilliant answer is you don't. You don't try to slow down the F1 car, and you don't try to speed up the snow chains. No, you change the architecture of the entire racetrack. And here is the breakthrough idea. It's genius. Instead of trying to certify the entire, massive, constantly changing Linux kernel, which is, let's be honest, an impossible task, you decouple safety from it completely. You basically build a wall. You create a dedicated, isolated safety layer that can run right alongside Linux on the very same hardware. Now, this is done through what they call the 3 pillars of isolation. First up is spatial isolation. Think of it like a hypervisor building these virtual walls in the computer's memory, so Linux can't ever touch or mess with the safety-critical stuff. Second is temporal isolation. Here, a safety monitor acts like a watchdog, making absolutely sure that a critical function, like, say, braking, is never ever delayed by something non-critical, like you changing a song. And finally, you've got communication integrity, which just makes sure that any message passed between these two zones is authentic and hasn't been tampered with. To really understand this pretty complex defense system, the source material uses an absolutely brilliant analogy: a medieval castle. So the defense starts in Act 1 building the foundation. The second you turn the car on, a process called Secure Boot acts like the first guard at the gate, checking the integrity of the castle's very foundation. Then, a second guard, Safe Bootstrap, verifies the operating system itself. Finally, data encryption builds these massive, impenetrable walls around all the stored info. The point is, the castle is secure before anyone is even allowed inside. Okay, now we're inside the castle. Here, we meet Tuxet, who represents Linux. She's this brilliant, powerful royal advisor, but she's also super complex and can't be 100% trusted. And that's exactly why we have Lisa, the safety monitor, acting as the captain of the guard. Lisa operates from her own separate, totally secure tower, and her entire job is to constantly watch what Tuxet is doing to make sure the kingdom's most critical functions are never, ever compromised. And this brings us to Act 3, the Long War. See, outside the castle walls, there's Black Hood, the hacker, an ever-present, constantly evolving threat. To fight this continuous battle, we have another advisor, Patchett. He's in charge of over-the-air, or OTA, updates, and his job is to constantly reinforce the castle's defenses for the car's entire 15-year life, making sure those walls never, ever crumble. So, okay, we've gone to all this trouble to defend our digital castle. What's the actual payoff? Well, the real-world benefits here are frankly game-changing. It all comes down to this one number, 50%. By adopting this whole isolated architecture, car makers can cut their research and development cycle and their time to market in half. I mean, that is a monumental advantage in such a competitive industry. Let's just compare the old way of doing things with a traditional closed-off operating system to this new open-source approach. You go from a black box system that nobody can see into to one that's transparent and secure by its very design. You go from desperately hunting for niche, expensive experts to tapping into a global talent pool. And you move from these huge upfront licensing costs to a much more flexible pay-as-you-scale model. But maybe the biggest accelerator of all is the shift left strategy. Now, it's called shift left because you're literally moving software development way earlier on the project timeline. Because the entire environment can be copied in the cloud, your engineers can start writing and testing software a full 6 to 12 months before the physical computer chip is even manufactured. This just completely obliterates hardware delays. It's a total game changer for speed. Which, brings us right back to where we started. The car isn't just a way to get from A to B anymore. It's a powerful, secure, constantly updatable platform. It's that computer on wheels, finally ready for its own app store. So the final question isn't about horsepower or miles per gallon anymore. It's this. If your car is now a platform, what app would you build first?